So, we were talking about breath analysis specs, right. So, there are, before we go to the optical techniques, there are various approaches. Of course, mass spectroscopy is one approach, then semiconductor based sensing, okay, using a conductive layer we can we can capture the information, should be positioned, okay, using conductive based layer, okay, we can do the sensing. And optical based sensing is developing very fast for such analysis, breath gas analysis, because it is having various advantages in terms of it is possible to measure real time measurements are possible, small volume of samples is good enough to extract the information related to different types of species trace gases present in human breath. We can use various techniques such as tunable diode laser based cavity ring down, optical frequency, photoacoustic spectroscopy, etc. We will try to see how they are being used. And there is one more approach which is ion mobility sensor. It is based on differential measurement of ions based on how they propagate. Of course, we are not going into those, we will not go into details, but it is basically we can ionize some of the gases and then we apply a certain type of radio frequency electrical field such a way that the ions will propagate depending upon their mobility, etc., will propagate either along a straight line or will get deviated and sorry, and will get filtered out. So, whichever are propagating along a straight line, a detector will be able to detect, and there will be a way that we can selectively capture the information about different trace gases, etc. So, that is ion mobility sensors which are used. They are also very useful and effective in trace gas sensing. However, from the what shall I say, application point of view, clinical application point of view, etc., certainly optical based techniques are much more compact as well as usable. Okay. So, we will try to see with the simple approach. We know that in case of spectroscopy, what we say is the absorption based spectroscopy. Basically, we use very simple approach. Oh, so if this is the input, and we know the transmission, okay, from input and output, we can capture the information about a particular trace gas which has absorption band matching with this input wavelength. So, what we need is we have already learned this absorption based technique and absorption based measurement technique. Now, in this case, the challenge is in case of such absorption based measurement technique, what we are proposing for measuring the trace gases, the challenge is as you know that the concentration of the trace gas, what we want to measure, okay, what we want to measure in concentration is very small, okay, is negligible, very small, maybe few ppm order or less than sub ppm order, okay, very small concentration is a challenge. Okay. So, now we know for a particular absorption species with a particular wavelength, what we select, sigma is fixed, and L is the length of this cavity. which is is one parameter, but for a given cell it is fixed. So, if n is very small, it becomes challenging in order to improve this measurement. Why? Because you know the sensitivity, which is nothing but I t lambda by I 0 lambda, or if you take this natural log is minus sigma lambda into n into L, and you know what we are measuring is this signal, isn't it? I transmitted with intensity and input intensity. Now, input intensity will be of a certain level, and if the absorption is very small, the change in the input intensity will be very small. So, what will happen, detector should be able to distinguish or resolve the transmitted intensity change, a small change in the input intensity in the form of this change in the transmission intensity with respect to small amount of small concentration of any trace gas. So, as to improve this, the obvious approach would be So, if I rewrite this equation, I transmitted lambda upon I 0 lambda, in order to improve this measurement resolution in terms of transmission intensity, change in transmission intensity should be large enough, then we will be able to easily estimate the small this concentration change as well. Okay. So, one approach is I cannot change sigma lambda. Of course, I can have sigma lambda as large as possible, okay, in order to improve this sensitivity. Or how is it possible? By selecting an absorption wavelength at corresponding to which the sigma values are large enough. So, sigma value will depend upon fundamental let us say different vibration and rotational band and electronic absorption bands. So, if there is a fundamental frequency corresponding to that, it may have certain absorption, it may have different other overtones, maybe nu 2, nu 1 plus nu 2, etc. All this corresponding to all these different frequencies or wavelengths, it will have sigma value. We can select a particular wavelength or a frequency corresponding to which the sigma value is large enough. Okay. So, that can be done. However, it may also have a limitation, because it depends upon the wavelength range for which the optical source should be available. If the wavelength is, let us say 6 micrometer wavelength, 7 micrometer, we may be having optical sources based on quantum cascade lasers or diode lasers. However, if we are looking for some other wavelengths where the optical source may not be available, then this is limited by the available wavelength, okay, the sigma lambda. So, sigma lambda is now known or fixed for a given wavelength or for a selected wavelength, and n is very small. We want to improve this IT transmission as much as possible, so that even with a very small amount of n, the difference, the ratio, this difference should be large enough in terms of change in this value, transmission value. So, how to increase? By increasing the length L. So, how will we increase the length is by using a multi-pass cell. Okay. If I, let us say this is single pass cell with length L, and so we know correspondingly what will be, we know for given L, for given sigma value, we can, based on the input intensity and output intensity, input intensity and output intensity, we will be able to capture n value. However, as I told you, if n is very small, absorption is going to be very small. So, the transmission intensity will not change so much based on right with respect to I 0 lambda. So, the measurement sensitivity will get affected. To improve this, we can use multipass cell. That means, the light will pass through multiple times, okay, and we capture the information. Oh, so let's say input is from here, okay, and let's say we measure the transmitted intensity over here, okay, detector is kept here, and let's say there is a mirror over here. So, that light will keep on right reflecting multipass. So, now the length right of this right measurement system will increase by 4-fold, right, L1 again, right, L1 L1 approximately, right. If this angle is very small, approximately the length remaining same, it will be 4 times. So, my transmission characteristics I t lambda now is right 4 times n, is not it. So, automatically even with a very small concentration, right, the intensity ratio is going to alter a large by a large amount. So, this is a very obvious right approach. So, multipass cell can be used in this case. Okay. There is so this is quite easy. We can have spatial design this cell such a way that it allows number of passes, multiple passes. Okay. So, there are such trace gas sensing cells available which can allow 32 passes, 64 passes, multiple. Okay. Automatically the path length increases, right. When path length increases, right, transmission characteristics accordingly will get change based on the absorption as well. Okay. Are you right? Concentration is not going to change what we are want to measure, but still this increase in path length will automatically involve more and more absorption. So, the transmitted intensity will change. Okay. So, indirectly, right, we are increasing the sensitivity of this measurement. Now, if you just if you can recall how laser system works, let us say there is a mirror, there is an optical amplifier, there is another mirror, right, feedback is this. So, we pump this crystal, we pump right, pumping is there and the crystal provides laser output at a particular wavelength, right. Now, in this laser cavity the number of passes are many. That means, this can also act as a multipass laser, right, cavity. In this, let us say if my optical crystal or some other right material amplifying medium, the output wavelength matches with the absorption of the species of interest, then let us say if I put a gas cell, okay, with the gas filled, right, some gas filled whose right absorption wavelength matches with laser output wavelength, then what will you observe? See this light lambda at which the absorption is taking place, which is emitted by through stimulated emission emitted by this crystal will keep on right moving. So, multipass cell, it becomes a multipass cell, right, with a gas cell of length L will allow us to measure a trace gas. But here the condition is this is intra cavity absorption technique, is not it? It is intra cavity, within the laser cavity you are incorporating the species, gas species of interest, which you whose absorption wavelength is matching with this laser, right, system output wavelength, and absorption concentration of this trace gas is measured. Okay. So, intra cavity approach, but the main important thing is it's the absorption wavelength of this gas species should match, then only it is possible. Okay. So, it has been tried out even with optical fiber base. So, instead of a amplifying medium being a crystal, I can have an optical fiber which is acting as which is, let us say, erbium doped fiber. Okay, erbium doped fiber, quartz fiber, okay, quartz, erbium doped quartz fiber, and laser cavity, it is pumped by some light source, then it becomes, right, with a feedback it can emit a laser wavelength around 1.5 micrometer, and it can be tuned to certain range, wavelength can be tuned, and right, how will we tune, I will ask you in the next question. However, let us assume it can be tuned, that means output wavelength can vary between 1.5 to 1. Let us say 6 micrometer or so, little less than that, but let us say. Now, in this wavelength range, let us say CO2 has an absorption band, okay. Acetylene has an absorption band, okay, around 1.55 or 55 micrometer, okay, around 1.57 micrometer or so, it has an absorption. Okay. Ammonia has an absorption band around 1.5 micrometer. Okay. They have various absorption bands. Now, if I tune this wavelength of this fiber laser to 1.55 micrometer, I put one gas cell. Okay. So, this is erbium doped, okay, quartz fiber pumped by some means to emit wavelength between 1.5 and 1.6 micrometer, and the gas cell is here with a length L, which is filled with acetylene gas, let us assume, or even CO2. Okay. And if this wavelength is matched with 1.55 micrometer, then we will observe, due to the presence of acetylene, the output from here will vary. Okay. Fiber laser output, in the absence of acetylene, we may get some output, right, and in the presence of acetylene, we will get some other output, right, and this will indirectly be useful to measure very small concentration of sub ppm order, because the laser is going to right, the light in this, right, cavity is going to oscillate many number of times. Hence, the optical path length is going in this through this medium will be very large, right, that is why. Now, one question for you, just that how will you tune this laser, erbium doped quartz laser, how will you tune? Tuning means I want to change the wavelength, right. Maybe I want 1.5 micrometer for 5 micrometer for acetylene, but now I want to measure ammonia. So, I will have to tune the laser to 1.5 micrometer, okay. Or I want to measure CO2, then I will have to tune the laser to 1.6 or 1.7 micrometer, 1.56 or 7 micrometer. You may ask why to tune to this particular wavelengths, that we have already covered, that there are different absorption bands depending upon fundamental frequencies, overtones, etc., and the wavelengths which I told you, there some of these absorption bands are falling. Okay. So, if you right now how will you tune the laser right to this particular wavelength? You know that when laser oscillates, it is oscillating with a right particular frequency depending upon the cavity configuration. The question is how will you tune here in this case? So, if I change the cavity length, it will not be able to see, it will have multiple modes, right. So, we already learned that this laser medium has a very broad gain bandwidth from let us say 1.5 micrometer to 1.6 micrometer. Okay. So, we know cavity length determines the mode spacing, correct, it determines the mode spacing, and if I change the cavity length, this mode spacing may slightly change, correct, but the frequency with which it is going to oscillate, right, maybe a certain frequency where the gain is large enough, it will oscillate anyway. I want to, and so laser output will look like this. If whichever frequencies are beyond threshold will all oscillate. Okay. So, there will be different frequencies, and cavity length increase may shift this frequency by small amount, but there will be many such frequencies. Okay. Right, and I will have to tune, and it is so small change because the length of this fiber will be large enough, right, long enough. So, C by 2 L, very small change in L will not change the frequency by large amount. Okay. So, although what Manikandan has suggested is fine, but it has a very limited tuning range. Okay. So, what can we do so that this can change? So, of course, try to recall that we can use external grating fiber grating structure and provide the feedback, right, and tune the mirror and change the angle. We have learnt, right, how to tune the laser wavelength. Please try to recall that, or use fiber break grating, right, change the grating period by heating or by stretching the grating period. Okay. So, fiber break grating, by changing the grating period, the reflected wavelength is going to alter, is not it? Can you recall, right? So, we can make use of such fiber break grating or a external cavity grating structure to provide the feedback and tune this. Okay. Right. So, right, this is the way that we can tune and obtain the output, etc. Okay. So, now this is one approach. However, there is another approach to increase the cavity length as long as possible, as much as at the same time we do not rely on intensity measurement, direct absorption intensity measurement, but we rely on the temporal characteristics of this. Okay. So, so it is something like this. Let us say there is a resonating cavity, this is a gas cell, okay, or the whole cavity is filled with a gas, this is a gas cell. Okay. This is a mirror M1, this is M2, and let us introduce a pulse flight, okay, temporal T with certain intensity, a pulse flight, I 0 lambda, everything has gone. Okay. So, just quickly I will introduce this, and next week we will do. So, I lambda and temporal pulse, right, passes through this cavity. Okay. Okay. So, what will you observe if this passes through the output intensity? So, this is I for given lambda, and at the time one pulse passes through So, transmitted signal will be through the cavity without anything, okay. And this is M1 mirror with M1, this is mirror M2, okay. This has a very high reflectivity, okay. Of course, there is some small loss, but reflectivity R1, this is reflectivity R2, okay. So, what will happen, next class we will see mathematically, but what will happen, this pulse what you have introduced here, the output will look like this every round trip, okay. This is L. So, this pulse goes through this, of course, due to high reflectivity etc., small amount of input intensity is getting coupled and small amount will come out. So, there will be right some small signal coming out, okay. Then second again it will go through multiple reflections. So, output will keep changing, and this is only one single pulse we have passed through, okay, single pulse within. So, output is going to be like this, this represents round trip time, okay, T is time, this is round trip time which is 2 L by C, right, will right, and this is intensity, transmitted intensity. So, you will see a decay characteristics, right. The input pulse has been fed and you are seeing that the output pulse is decaying, because that pulse will keep on reflecting inside, small output is coming out and slowly it will decay, because the pulse is no more after that, right. And if you send the second pulse after some time, again you will observe same, detector will observe the same decay characteristics like this, okay. Now, if I fill this cell with a gas, right, trace gas with sigma lambda matching with, right, absorption band is matching with this input intensity, right. What will I observe in terms of decay characteristics? Now, the decay will be fast, because every round trip the light intensity is also undergoing some absorption. When it passes through this gas cell, right, light it is undergoing absorption. So, what will happen? It will decay very fast, and if it decays very fast, the decay time will indicate the concentration change, is the idea, okay. So, we are not measuring the intensity ratio, right, it is now irrespective of whatever may be the intensity, input intensity, right, even if it changes input intensity does not matter, the decay characteristics is independent of the input intensity, it only observes the losses in the cavity, okay. The losses are determined by mirror losses, okay, reflection, every reflection there will be some loss, there will be some scattering and there will be absorption, okay. So, next class we will try to see those aspects. Today I am so sorry it did not work out quickly, I should have completed this, we would have gone to the next topic in fact, but sorry it is got delayed, okay. And yesterday also I had to check, right, because of some important meeting I had to cancel the class, okay. But we will try to see, we are little slow, I will require a couple of classes right to cover this, okay. So, we will try to see how best we can, maybe next week if possible, if all of you agree, maybe Wednesday class also if we can take and try to see that, okay. Thank you very much.